Hi, my name is Michael Sangillo, and I'm sorry I couldn't attend the session in person today. I hope we're all having a great time and are learning a lot. I'm a Darpa program manager in the Microsystems Technology Office, and I'm excited to kick off the additive manufacturing for advanced packaging and heterogeneous integration session today. At DARPA, we're looking at new ways to leverage additive manufacturing for a variety of defense and commercial applications. I'll present one of those applications here today, and that's integrating additive manufacturing into advanced 3D packaging. Additive manufacturing started back in the 1980s. It's the process of joining materials together to make 3D parts. AM has had a huge impact on how we manufacture components, devices, and systems around the world, most notably on the mechanical or structural side of manufacturing. And here's an example on the left of something like that. More recently, in the past decade, emerging materials and deposition methods have opened the door for commercial companies to fabricate electronics, and impressive ones at that. For example, the PCB that's being shown on the right, flexible electronics, or conformal antennas being printed in things like mobile devices. Manufacturing has enabled a huge amount of capabilities in larger scale things. Where things start to get really challenging in AM is in the advanced packaging side of things. On the left side is a chart that shows a red trend line for advanced packaging length scales. By 2025, we'll be in the near micron scale for conductor and insulator line and space. At this scale, rheology and adhesion and cohesion start to play a part. If you have droplets or you have liquids, they will attach to defects, even defects that are less than a micron in scale. And the reason for that is that the droplet or the liquid itself will try to minimize its surface tension and will just attach to it. What this means is that our materials that we're depositing to actually need to be very clean to make sure that we get limited defects or no defects in our microelectronics of the future. The right shows you a sense for a 3D heterogeneous integrated package, 3D-HI. It's a stack up of chiplets where length scales at the micron territory will be present. DARPA is driving this innovation and working with the research community to make something like this a reality. One thing that I want to note here is 3D-HI is currently planar, and AM, the benefits of it is to enable 3D non-planar designs. I envision a future where advanced packages include non-planar assembly and conductor paths. DARPA program manager, I've been fortunate to speak with numerous members of the additive manufacturing and advanced packaging community. This is an image that shows a research paper out of a German university, KIT, that I think best represents the state of the art. It's packed with information regarding print resolution and throughput for different deposition techniques and different materials. Looking towards the center, we have the 1 to 10 cubic micron voxel size. This is roughly the region where advanced packaging length scales are heading. And think of the voxel as a 3D pixel, the material that you would be depositing. This is a little bit more complicated, but the diagonal lines are the next dimension of interest. The diagonal lines show the measured throughput of each one of these experiments. The line that passes through the yellow ellipse is approximately 100,000 cubic microns per second. And this is the region where we believe that is relevant to printing advanced interconnects on the order of hours. We expect advanced packages to have between 5 and 8 interconnects, resulting in about a 1-day turnaround time for printing the interconnects and assembling the advanced package. One thing you'll notice here too is in the yellow ellipse, there aren't a lot of experiments or demonstrations of deposition techniques that meet the throughput and the resolutions that we need. There's more. This is a view of where I'd like to see things go. The vision is to shrink an entire packaging floor of equipment into a highly versatile machine with all the integral components to fabricate advanced 3D electronic packages. Imagine loading a machine with AM materials, chiplets, packaging, and substrates, as well as digital design files, and then sometime later, a freshly made advanced package arrives for test and usage. I think we're rounding the corner on this being a possibility in the near future, and this opens the door for in-house rapid prototyping, fabrication of high-mix, low-volume devices at universities, small businesses, and larger manufacturing facilities. The possibilities are broad, and in truth, I don't think that we've thought of all the ways that AM will impact microelectronics yet. The best is yet to come. So let's dig a little bit deeper into the workflow. There are four major steps or states in this machine. The first is chiplet assembly and packaging. This is where components like package casing, substrates, or chiplets are pick and placed in location. The next step is the AM step, where the interconnect materials are printed and attached to the I/O of the active electronics. We're conceptually building a machine that is capable of producing any shape interconnect or placing chiplets in any position. After the conductor and insulator material has been deposited, we need to do an online metrology check. This is a critical step in additive manufacturing of electronics. We need to check to make sure that things were put in the right place, that there aren't any defects or anything that needs to be corrected. In some cases, we will need to correct defects in a post-processing step, or even polish materials to achieve good surface roughness for signals that require high signal integrity, such as multi-gigahertz signals. This process goes back and forth until it's complete and the machine outputs an advanced package. But what about some of the technical challenges that need to be overcome for something like this to become a reality? From all of my conversations and research, we need to start at the basics, and that's materials and deposition methods. To date, I haven't found a person that's told me that materials are reliable. This includes quality control, where materials have small differences in electrical properties between even batches of the same manufacturer. They also appear to have a shelf life, where some materials age through oxidation or other similar processes. There's a lot more work that needs to be done in quality control of reliable stock electronic additive manufacturing materials. The next part is deposition. As I showed a few slides ago, there aren't a lot of technologies or approaches that are capable of achieving the resolution and the throughput necessary for AM advanced packaging. I believe the path forward is likely a multi-technique deposition approach, where we're using sort of the best of different things for either the conductor or the insulator material. They're likely going to require different techniques. The next part here is 3D design tools. If we're going to move into a non-planar conductor space, we need to start thinking about how we synthesize layout, where signal integrity and match latency paths are just a few of the objective functions that are being optimized in this sort of multi-objective optimization process. If we have a curved conductor, we need it to look electrically flat, so that likely will require some interesting tricks in the dielectric permittivity as well. The manufacturing system, if we're building non-planar assemblies, we will need to have 6 degrees of freedom in picking and placing components and package devices. Additionally, the position error of that is we head into sort of a 10 micron pitch. It's going to have to be very fine, likely sub-micron. Online metrology, we spoke about that a little bit already. As the deposition is occurring, there likely will be defects. This process is not going to be perfect. And so what we want to do is develop methods to detect that event and to come up with a mitigation plan. And that mitigation plan likely is a post-processing step, where you're using things to etch away material or to polish material that's not perfectly smooth or sufficiently smooth. Among the challenges discussed in the previous slide, some of the leading methods of AM don't quite cut it for high-density interconnects that are required in our future advanced packages. For example, aerosolized jet printing. It prints nanoparticle-based inks for the most part. There's some reactive inks as well. This method is fantastic for printing conformal conductor paths on non-planar surfaces. Think of mobile antenna devices, right? But there are issues with this approach for high-density interconnects, and specifically interconnects that are carrying multi-gigahertz signals. The surfaces are often rough, which leads to insertion loss for high-frequency signals. Depending on the material composition in the machine settings, you can get things like overspray at the micron scale. As you can see here, you've got a number of satellite droplets that I would consider to be defects and insufficient for advanced packages. Droplet-based approaches are tough at the scale. As we discussed earlier, rheological forces start to play in here, where it wants to attach to anything, including defects, and its objective is just to reduce surface tension. So, there's a huge hurdle to be overcome if aerosolized jet printing is going to play in advanced packages. multi-material compatibility. This is a problem that the electronics community has already tackled, but it needs to happen again, and specifically because we're using new AM materials and new deposition methods. The challenge here is that we want to bond dissimilar materials like insulators and conductors that have different coefficients of thermal expansion, or CTE. The difference in CTE causes materials to expand at different rates during operational temperatures, which results in high stress at that interface layer. So the graphic on the left here is showing an example of that, where the low CTE material is expanding or has stress at lower levels, and the high CTE material, such as the insulator, has higher stress. If the stress is high enough at that interface layer, that could lead to delamination and most likely intermittent or permanent circuit failure. On the bottom right is just an example of copper being 3D printed onto a substrate that was then put through thermal cycles, and you can see the delamination clearly that's occurring there. This is going to happen in our advanced packages, and it's something that we need to tackle immediately. This is a real reliability problem. Because we're tackling the problem again, I think there are lessons that can be learned from traditional manufacturing and apply them here as well. A perfect example might be adding an interface layer in between that improves adhesion and CTE matching. So sort of sandwiching a material that helps to blend that CTE. Porosity and surface roughness, they're the enemy of high performance electronics and are very common in additive manufacturing. As we mentioned previously, the larger scale things that are being 3D printed don't really get affected as much by this kind of thing. But since we are talking about surface roughnesses of 100 nanometers or more actually causing issues to things, multi-gigahertz signals, this is a real issue, and it's something that needs to be addressed as well. This is an image of a metal particle-based approach where the metal is sintered at high temperatures to melt the particles together or to coalesce them. Generally speaking, the higher the temperature, the lower the porosity achieved. From a manufacturing repeatability and reliability perspective, if we used the current AM approaches, the locations of the voids are random, resulting in no two advanced packages having identical interconnects. That could also be a challenge from a repeatability perspective. Understanding that some of the circuits have more electrical tolerance than others, in some cases, this porosity or even surface roughness might be okay for things that are carrying DC power, but not broadly across the advanced packaging space. As I mentioned earlier, droplet-based inks and particle-based approaches have a huge hurdle to jump over. And this is exactly the reason why, because it results in materials that are not the hardest challenges that are out there to realize technologies that change the world. Here are some new opportunities that become possible if we can overcome some of the technical challenges that we previously discussed. With AM-based techniques, we open the door to curved electronics for more compact sensors or highly constrained volumes, like that exist in smartwatches, for example, where there's a lot of processing power packed in there, but there are some serious mechanical volumetric challenges in how we squish electronics into the empty space. Next, we can imagine a world where we have the opportunity to rapid prototype high mix, low volume advanced packages and bring designers, specifically hardware designers, into the agile hardware development regime, much like software development in the agile space. This enables hardware designers to very quickly iterate on new design concepts instead of waiting for months to get their advanced package back. So something like this, we believe, could get us into the territory of day or days of advanced packaging turnaround times. Finally, micron coax. I've spent a large part of my career in the RF domain, and coax is key to transmitting signals over longer interconnect lengths, where we require minimal insertion loss for high frequency signals. With additive manufacturing, we open the door to potentially printing 3D micron coax inside of advanced packages to enable those sort of 3D conductor paths where signal integrity is critical, and we need to be in the non-planar space to kind of get around if I were asked what is the one thing that I would do to tackle AM-based methods in support of advanced packaging, I'd say something along these lines. I'd start looking at photo-based additive manufacturing techniques. Light's an incredible tool, and I think there are a lot of lessons that we can learn from planar photolithography developments of the past that we can leverage moving forward. As a thought exercise, I would start to imagine a non-planar photolithography source and reactive materials that realize near micron 3D circuit interconnects for advanced packaging. So this likely will require high resolution light sources and specifically maskless. There's something there, and I'm interested in exploring that a little bit. And finally, thank you for your time today. I hope you enjoy the remainder of the session. And if you're interested in learning more about our interests at Darpa in additive manufacturing for electronics or microelectronics, please feel free to reach out to me. My email is michael.sangillo@darpa.mil. Thank you all. Hope you have a good day.